Have you ever pondered over how the kilogram, a unit we use daily, is defined? It's a question that most of us probably haven't given much thought to, but the answer is quite intriguing. The kilogram, as we know it, has a rich history. It's been with us since the late 18th century, when it was first introduced as a part of the metric system. Back then, the kilogram was defined as the mass of 1 liter of water at the temperature of melting ice. However, this definition was not practical for precise measurements, leading to the creation of a more tangible standard, a cylinder made of platinum and iridium, stored under 3 bell jars in a vault outside of Paris, France. This cylinder, known as the international prototype of the kilogram, or Le Grand K, has been the global standard for the kilogram for over a century. But Le Grand K has its issues. Over time, even with the utmost care, the mass of the cylinder can change. Microscopic particles can adhere to the surface, or tiny amounts can wear away. These minute changes might not seem like much, but in the world of science, precision is paramount. A fluctuation in the mass of the kilogram can impact scientific research, manufacturing processes, and even international trade. These potential changes pose a significant problem. For a unit of measurement to be reliable, it needs to be constant, unchanging over time and space. The kilogram, as defined by Le Grand K, simply doesn't meet this requirement. It's not constant. It's not universally accessible. And with every passing year, the likelihood of its mass changing, even ever so slightly, increases. So, we're left with a conundrum. We need a kilogram that's constant, reliable, and universally accessible. We need a definition that's not tied to a physical object that can change over time. But how do we achieve that? So, how can we redefine the kilogram in a way that's constant, reliable, and universally accessible? A clue to the answer lies in the realm of quantum physics, in a concept known as the Planck constant. But that's a tale for the next scene. Enter the Planck constant, a fundamental concept in the world of physics. The Planck constant, denoted by the letter H, is a central figure in the realm of quantum mechanics. Quantum mechanics, for those who don't know, is the branch of physics that describes the world at the incredibly small scale of atoms and subatomic particles. The Planck constant was discovered by none other than the German physicist Max Planck at the turn of the 20th century. Max Planck was trying to solve a puzzle known as the violet catastrophe, a problem concerning the distribution of energy in a radiating body, like a hot iron poker. During his research, Planck made a revolutionary move. He suggested that energy, instead of being continuous, comes in discrete packets, which he called quanta. This was a radical shift from the classical view of physics and marked the birth of quantum mechanics. The Planck constant is the proportionality constant that relates the energy of these quanta to the frequency of their associated electromagnetic wave. In simpler terms, it's the amount of energy carried by a single particle of light, a photon, for each cycle of its wave. The value of the Planck constant is incredibly small, approximately 6.626 times 10 to the negative 34 joule seconds. The unit of the Planck constant is joule seconds, a unit that combines energy, joules, and time, seconds. It's a reflection of the inherent relationship between energy and time, a fundamental concept in quantum mechanics. So, we've established the Planck constant as a cornerstone of quantum mechanics, a quantity that underpins the behavior of the tiniest particles in our universe. A quantity so precise, so fundamental, that it's been measured with an uncertainty of just 13 parts in a billion. But, you might ask, what does this have to do with the kilogram? Here's where it gets interesting. The Planck constant can help us redefine the kilogram. Let's delve into the fascinating world of the Kibble balance experiment. This ingenious experiment is the key to linking the kilogram with the Planck constant. The Kibble balance is a highly precise scale designed to measure mechanical power in terms of electrical power. Now, you might wonder how a scale could possibly measure power. The magic lies in the balance's 2 modes of operation. In the first mode, the Kibble balance uses electrical power to counteract the weight of a test mass. This gives us an equation linking the gravitational force on the mass, the voltage, and the current in the balance. In the second mode, the balance measures the velocity of the moving coil in a magnetic field. This introduces the Planck constant into our equation. as the electrical power can be expressed in terms of frequency, and frequency is linked to energy through the Planck constant. So we are left with two equations, both describing the same physical situation, but expressed in different units, one mechanical, the other electrical. By setting these two equations equal to each other, we can solve for the mass of the test object in terms of the Planck constant, electrical quantities, and a few fundamental constants of nature. And voila! The kilogram is no longer a lump of metal stored in a vault in France, but a value derived from the Planck constant, a fundamental constant of nature. This means that we can, in principle, reproduce the kilogram anywhere in the universe, as long as we can measure electrical quantities accurately and have a good handle on the value of the Planck constant. So, we've established a connection between the kilogram and the Planck constant. But how exactly does this redefine the kilogram? The Planck constant doesn't just link to the kilogram, it redefines it. A profound statement indeed, but how does this transformation take place? Let's delve into it. In 2019, the scientific world witnessed a significant shift. The International System of Units, or SI, made an official change to the definition of the kilogram. It was no longer defined by the mass of the international prototype of the kilogram, a cylinder of platinum and iridium stored in France. Instead, it was tied to the Planck constant, a fundamental constant of nature. This change didn't alter the mass of a kilogram in any way. What it did was to redefine the way we understand and measure it. The Planck constant, a figure central to quantum mechanics, became the new anchor point. Its value, approximately 6.626 times 10 to the negative 34 joule-seconds, is now the foundation of the kilogram's definition. So, why was this change necessary? Well, the main benefit is the universality of this new definition. The Planck constant holds the same value, no matter where you are in the universe. It doesn't change with time or location, unlike the physical artifact that was used previously. This means that the definition of the kilogram is now independent of any physical object. It's stable, reliable, and immune to any potential damage or loss. Additionally, this redefinition makes the kilogram consistent with the other 6 base SI units. They're all defined by fundamental constants of nature, making the system more coherent and interrelated. This change also paves the way for more precise and accurate measurements, fostering advancements in science and technology. So, while it might seem like a simple change in definition, the implications are far-reaching. The kilogram, as we know it, has been revolutionized, all thanks to the Planck constant. As we move forward, this new definition will continue to shape our understanding of the world around us, proving that even in the realm of constants, change is the only true constant. The redefinition of the kilogram has far-reaching implications. This isn't just a minor tweak in a dusty textbook, it's a monumental shift, impacting multiple fields from the theoretical to the practical. Let's start with physics and engineering. The old kilogram was a physical object, a lump of metal in France. But what if it changed? Gained a molecule here? Lost an atom there? Even the tiniest of changes could throw off precise calculations. Now, with the kilogram tied to the Planck constant, those worries are gone. This new standard isn't going anywhere. It's as constant as the speed of light. But it's not just about scientific accuracy. There are practical, everyday implications too. Consider trade and commerce. We trade goods based on their weight. Imagine buying a kilogram of flour, only to find that your kilogram is different from the baker's kilogram. Chaos, right? But with the new kilogram, we've got a universal standard. Everyone's kilogram is the same, from Tokyo to Toronto. The new kilogram also has implications for technology and innovation. As we push the boundaries of science, venturing into realms of nanotechnology and quantum computing, we need standards that can keep up. The old kilogram, tied to a physical object, just wasn't cutting it. The new kilogram, rooted in quantum physics, is ready for whatever the future brings. And let's not forget about education. The new kilogram is a fantastic teaching tool. It's a real-life example of quantum physics in action. It helps students see the relevance of these abstract concepts, bringing quantum physics out of the realm of the theoretical and into the everyday. So, The next time you use the kilogram, remember, you're not just dealing with a unit of mass, you're dealing with a piece of quantum physics. It's a testament to human ingenuity, a symbol of our quest for knowledge. The kilogram might seem simple, but it carries with it the weight of scientific progress.